Hello everyone, this is Professor Roman. Welcome to the 46th video in my video lecture series, An Introduction to Discrete Mathematics. In this video, I'm going to talk about two applications of trees, binary search trees and Huffman codes. So let's start with binary search trees. Suppose we have a large collection of words that we want to store in the memory of a computer. And we want to do it in such a way that two conditions hold. First, it's easy to determine whether or not a word is in the collection. I guess I should say relatively easy. And if a word is not in the collection, it can be relatively easily added to the collection. Well, two possibilities come to mind immediately. We could store the words in alphabetical order in successive memory locations, and that's shown here in this figure. This would make it very easy to tell whether or not a word is in the collection, relatively easy. However, it would be very difficult to add a new word to the collection because in general we have to move a lot of words, shift all the words that come after the new word in alphabetical order down one memory location in the computer, and that's a pain. On the other hand, we could just place the words in successive memory locations in any order whatsoever. Then it would be very easy to add a new word to the collection, but very difficult to find a word in the collection. So these two options are extremes, and neither one is really very good. But there is an alternative that involves the use of trees. And the idea is to store the words in the collection at the vertices of a tree. And in this way, the data structure that we create is two-dimensional rather than the one-dimensional list that I've just talked about. And the extra dimension makes the two goals that we're interested in much more accessible. So let me describe the process with an example. Suppose that our collection of words are the words in this sentence. Graph theory is a very interesting subject. Well, we begin by choosing any of the words from the collection, say the word interesting, labeling a vertex with that word, and then connecting two more vertices with edges. So the two new vertices are leaves. Then we take another word from the collection, any one at all, say the word theory. And since this word comes after the word interesting in alphabetical order, we label the right-hand vertex with the word theory, and we add two more leaves. Then we choose another word, subject. Start at the top, compare subject to interesting. Subject comes after the word interesting in alphabetical order, so we move down to the right. Compare subject to theory. Subject comes before theory in alphabetical order, so we move to the left, label the vertex subject, and add two new children. Well, now, hopefully the pattern is pretty clear. In order to add another word from the collection to the graph, to the tree, we start at the top of the tree and repeatedly compare the new word with the labels of the existing vertices if the word comes before a given label, when we encounter it before an alphabetical order, we move down the graph one edge to the left. If the word comes after the word in the given label, we move down the graph to the right. And we repeat that until we arrive at an unlabeled vertex, a leaf, label it with the new word, and add two new unlabeled child vertices, at that point where we added the new word. So you might want to stop and finish this this graph, this tree. This is what my version looked like. It's possible to construct different trees because it depends on how you choose the words in the collection, in what order you choose them. And there's some effort made to create as flat a tree as possible because that has shorter paths. But I'm not going to discuss that issue. This graph is called a binary search tree. Storing a collection of words at the vertices of a binary search tree is a very effective way to achieve the two goals I talked about earlier. Given a new word, we can determine if that word is already in the collection, and if it's not, add it to the collection in one step. We just add the word to the tree, or attempt to add it to the tree in the manner I've just described. If we encounter a vertex with that word already, we know the word is in the tree, we know where to find it. If we get to a leaf and we didn't encounter the word, then we label that leaf with the new word and add the child vertices. Simple. So there are two reasons why this procedure is very effective. First, we can decide whether or not a new word is in the collection without having to compare it to every word in the collection, or even half the words in general. Depends on the tree. Could be quite a bit fewer comparisons required for a very flat, wide binary search tree. So we only need to compare the word to the words that are in the path that must be followed in attempting to add the word to the tree. It's only that one path that we're concerned with. Second, when we add a new word to the tree, none of the other words need be moved because the new word ends up at the bottom of the path we followed. So we don't touch any of the other words that are already in the tree. Of course, binary search trees can be used to store other types of data than words. Any data that is ordered can be stored in a binary search tree. So this is a really superb example of the use of trees in computer science, in the theory of data structures. Okay. Now, as we've just seen, it's pretty easy to add a new item, let's say, to a binary search tree. Deleting an item is a bit more complicated. It's not too bad. It looks a little messy, but it's really not bad once you think about it. So let's go over that. So looking at this figure, we have a tree, a binary search tree. And let's say this tree, we'll call it T, is a binary search tree for an ordered set, script S. It's right here. The top vertex of a binary search tree is called the root of the tree. And as I've discussed before, a leaf is a vertex of degree 1. and the edge that connects to a leaf we'll call it a leaf edge. The leaves in a binary search tree are the only vertices that are not labeled with elements from the set S. Now, a couple more bits of terminology referring to this figure. If we ignore the leaves, a vertex, a non-leaf vertex of a binary tree T, such as this vertex little t here, may have both a left child and a right child. So S is the left child of T and Y is the right child. When we discussed trees before, we never made a distinction between left and right, but now we must. Some vertices, however, have no children. For example, the vertex A here has no children. Remember, we're ignoring the leaves now, temporarily. Okay. The vertex P here has a right child, but no left child. Also, the label of the left child comes before the label of the parent. And the label of the right child, when there is one, comes after the label of the parent. The subtree of this binary search tree consisting of a left child and all of its descendants, including the leaves, is called the left child subtree of the vertex. So for the vertex T, the left child subtree is what's encircled here in red. It's the left child and all of its descendants. And similarly for the right child, which is circled here for the vertex T. Notice also that the smallest element of the underlying set S is found by starting at the root and moving left, only left, until we come to the last non-leaf vertex. So A here is the first element in the set S, the smallest element. If we want the largest element, we do something analogous. We move only to the right until we come to the last non-leaf vertex, in this case Y. So Y is the biggest element, the largest element in the set. The same thing works if we concentrate only on a subtree, let's say the red subtree here. If we want the smallest element among the labels of this subtree, we would start at the top and move left until we come to the last non-leaf vertex, which is P. So it works for subtrees as well. I know this is a lot. You're probably getting phased out a little bit here. Don't worry about it. If you need to review these terms, we'll come back. You can come back to them. So don't panic if it's too much to remember right now. Our goal here is to figure out how to remove an element from the set, underlying set, or in other words, remove its vertex from the binary search tree. Okay. So we have to take some cases depending on how many children that element has that we want to remove. So let's say we're wanting to remove X and X has no children. Then what we do is remove the label x from the vertex, not the vertex itself, but just the label, and then remove the two leaves and leaf edges connected to that vertex. So again, I know that it's hard to follow this, but if we look at an example, here is the vertex Q. It has no children. We want to remove Q. Yank out the label, yank out the leaves and the leaf edges. And what's left is in black, and we've removed Q. Okay. The no children case is the simplest one, but it's still hard to express in words, easy to express in pictures. If the vertex X has one child, then this is what we would do. And I'll just show you the picture. You can read the words yourself. If we want to remove the vertex B or the element B from the set and the tree, we will remove the label, remove the vertex, remove the two child edges, remove this vertex, and then move the subtree here, starting at A, up to B, well, what was called B. So did I say remove this vertex? I hope I did. We're removing the stuff in red, and then just moving the encircled part up to where B used to be. If we have two children, if X has two children, there are two ways we can delete X. So consider this tree. We want to remove the element T here. One way is to relabel this vertex by finding the largest vertex in the left child subtree. That would be U, because the left child subtree starts at S. To get the largest element, we move to the right until we can't go anymore. So that's U. So we'll relabel T U and then dump all this in red. So it'll look like this. Everything's in place. We've lost the red portion that used to be right here, and T is now labeled U. And you should spend a moment convincing yourself that this is still a binary search tree. We haven't screwed up the alphabetical ordering or the tree ordering. Okay. That's why we had to pick the largest vertex, the largest label in the subtree, and not the smallest one. We can't move P up here because that's going to louse things up, because then S is below P, but it's to the right. It's to the left, and that's no good. The alternative is to look at the right child subtree, take the smallest element, W, relabel the vertex or the label trying to get rid of, and then cut out these red portions, the vertices and edges. So this piece is gone, and you can see that Z has now been moved up. I didn't draw that, but here it is, moved up, and T is now labeled W, and that works too. So you got a couple of choices for deleting elements in this case. Well, that's all I had in mind to say about binary search trees. I hope you see that they are extremely useful as storage mechanisms for data, ordered data. They're very efficient. Okay. Well, the next item of business is Huffman codes. And despite what I said at the beginning of this video, and I don't feel like redoing that, I have a feeling I should postpone this to the next video. So far, we've run about 19 minutes, 20 minutes, and the Huffman codes is going to take some time to explain because I want to justify everything about what I say. And so let's end this video here, and we'll do the Huffman codes in the next video. So thank you for watching, and I do hope to see you in the next video.